Let's get back to basics. A quarter wave ground plane antenna. Let's build one, see why you need one, what to consider when tuning one on the vector network analyzer, and how a proper performing quarter wave ground plane antenna should work. This is me trying to make a very boring video somewhat entertaining and failing at it horribly and choking myself with smoke in the meantime. Hey everyone, welcome back. This week I thought we would catch up on the antenna tutorial from last week, but starting at the basics. And the basics is the good old quarter wave ground plane antenna or quarter wave monopole antenna. It's boring, but there's some tricks that you need to learn to make this antenna properly. And if you're serious about antennas, everybody should be building one of those antennas for every single set frequency that you test against, because you really should be using that antenna to measure all antenna performances against. It's just a very good antenna. And the reason why it's good is because it allows you so much flexibility in terms of tuning it and getting a proper impedance match, as well as getting it to be sensitive at the right frequencies. So without further ado, let's jump into it. If you go to the University of Guguletu, otherwise known as Google, and you just type in quarter wave ground plane antenna propagation, you'll start seeing the sort of patterns, and you can see the sort of donut. Now, a lot of people think that this antenna doesn't have gain, and there's arguments on both directions. We're not going to go into that today. The point is just, it's a great antenna as a reference antenna, and it is an omnidirectional antenna. So if you don't know what antenna to build or use in a certain frequency group, this is a damn good place to start. So if you type in quarter wave ground plane antenna calculator, this is just the first one that pops up. For some reason, Google favors this one. I think it's one of the oldest ones. I've used it for years. And there's many of them online. I'm not going to say which one is better and which one is worse. I'm just going to give you the basics and what to look for when we actually put it on the VNA. Stick around till the end, because there's one little trick that might be influencing your performance. So starting from the top, you just type in your frequency as desired in megahertz, your velocity factor. So your velocity factor is important because different materials like aluminium or steel or copper all have different velocity factors, and that just refers to how fast the signal propagates through the material itself. For me, I use a solid copper wire, 1.3 millimeters, and I know the velocity factor is around 9.8, but you can always tune this after the fact. So for now, I'm just going to start there, but if you used aluminium wire or something in that nature, I would start at 0.93 or 0.95. Then I'm going to work in millimeters, hit calculate, and what we'll see is it actually gives us two measurements. The one is the A and the other one is the B lengths. And if you scroll down, you'll see the actual ground plane image. So this is a two-dimensional image. You are actually supposed to have 4 of these B legs. Some people say 3 works, but I've just found that 4 works the best. And you'll see that they marked it at a 45-degree angle. It's actually not 45 degrees. It's something like 42 degrees, I think, or close to that. But because we can tune the antenna on the network analyzer or the vector network analyzer, it really doesn't play a role. It's just more of a guideline for what we need. So you can more or less take these numbers to heart. We will end up very close to these numbers, although some tweaking will be required and to be expected. It depends on the material, it depends on your soldering joints, it depends on a whole lot of things. So always use this as a fun reference. It's never going to be 100% accurate, but it's a very good place to start. Then we'll see our radials is 89.8 millimeters, and so on and so forth. Now, what I've done is actually jumped into Onshape, which is just one of my favorite tools to use for this type of thing. And I've created a little jig. Now, this jig uses a SMA connector in the middle to hold it in place while you solder it. Feel free to download this. It's on Thingiverse right now. Link will be in the description below. You can find it on my Thingiverse page along with all the other antenna designs. So without boring you to death, let's quickly jump over to the bench and actually start building this antenna. Right, so This is our main radial. Now you could have gotten just 5 that strip all the same length because we're going to cut them shorter on the actual test jig. But for now, this is just a great place to show you that you need 5 different lengths. Well, 5 pieces of 2 different lengths. So what I'm going to use is actually a Dremel to clean off the enamel. If you use wire that doesn't have the enamel, then good for you. I just use of what I have right now. So let's jump into that. Now, not to bore you guys, I'll speed this part up. Right, so we have our little jig, we have our SMA female connector, and I'm just going to plop that in like that. And what I generally do is I turn it so the corners actually face where my little spaces are. And just to get a bit of height off the table, what I like to do is plop this up onto something. So if I grab it like that, put this here, let's zoom you out, like that. So the first things I want to do is always go through and just tint or prep all of these corners. Now, this soldering iron is horrible, don't look at it, but it's an old soldering iron I use for antenna specifically. It's not my fine point for electronic work. So all I'll go through and just touch these up like that. Hope you can see that. So if I turn it like that, you just see that the corners are touched. And important note, we'll actually cut what remains off of these corners off. But the reason why I like to use through hole is because, as you can see there, the solder tends to flow upwards and gives you a better sort of real estate for the wire to grip against. So it gives you a stronger bond, and then you can just chop off what is remaining. And there's a good reason to chop off the rest, which we'll get into just now. And then what I'd like to do is just go ahead and they leave the metal bolts like half an inch or 10 millimeters protruding through this point. And what you're really doing is you're creating a little impedance cone around your center conductor. And that what ends up happening is electrically your center conductor actually starts looking a bit shorter or longer than what you are planning it for it to be. So 2 important things to note here is always remove that as far as possible, as you can see there. And second thing is, whatever you solder onto the middle core forms part of your antenna now. So in reality, that little section in the middle there, if I put my ruler in there, it's about 5 millimeters. So that is actually effectively extended my entire monopole now by 5 millimeters, and that'll be evident on the vector network analyzer. And that's why it's so important to actually have one of those devices handy, because any antenna you buy or you build without testing it is just as good as nothing, really, because the impedance matching changes for every single material that you use. And so, just for you to have a quick look, I'll give you some B-roll as well, but I don't know if you know that was 2 minutes or 5 minutes, but there you go. Quick and dirty, very simple. Now let's jump over to the VNA and see how this puppy works. Right, so first things first, if you don't know what a pocket VNA is, or VNA in general, it's a device to measure the network sensitivity and impedance matching. It can be used for antenna gain, testing, that sort of stuff. We're not going to get into that today. So what I always like to do is just attach it, and here's a little trick and a little tip for you. Always try and tune your antenna on the actual cable that you are going to be using in the field, whether it's a 1 meter, 2 meter, 4 meter cable. Without an actual baling attached there, you'll be surprised, even an antenna that claims to be 50 ohm, how it actually affects your antenna. Second tip, the space between my face and this device is far too close. You actually affect this antenna's field quite a bit by being this close to the antenna. So whenever you can, always try and be more than a meter away from your antenna when you tune it. So what I'm going to do right now is actually jump over to the software, and we'll just do a general scan. I calibrated my VNA a bit earlier, so we'll do a general scan from 1 megahertz to 1 gigahertz, and let's see where this antenna falls before we start tuning. And so at this stage we had the predefined marks as to what we've marked with the Sharpie, and what you can see on the screen is that we actually still about 50-60 megahertz off as to where we want to be, and that just shows you the error that's in the calculators. Now, it's not to say that the calculator is wrong, but the velocity factor, the type of materials that you're using, your calibration, and all of that stuff plays a role. And this is now where the need for VNA actually starts playing a role. So if we look at our intended frequency of 917 megahertz, I'm going to go ahead and actually add a marker just to make it simple or easier to view where we actually want to be. So if we set a frequency marker somewhere over there, 916 is close enough. This is now where the trick comes into tuning these antennas properly. What you want to do is always maintain that ratio of that your main or your main radiating element is just that slightly shorter than your radials. So what I'll continue to do now is millimeter by millimeter, trimming these shorter and always keeping this one just slightly shorter. And what this will actually allow us to do is see what our velocity factor is, which we can at least phase out one of the variables. All right, so as you can see, we're now in the 900s. Just a little bit of frequency shifted at more than 30 megahertz, so you have to be very careful when you get to this point. We're sitting at about 905 megahertz, which is still a bit low for where we want to be, but at least our desired frequency range is already within the bandwidth. So we could stop here theoretically if we wanted to, but I would like it to be as sensitive as possible on that specific bandwidth. So we are going to carry on cutting, but when you get to this stage, what you want to do is start thinking of your radials as completed, and just start trimming your main arterial or main element, radiating element down. If your ratio goes too far out of bounds, what you'll start noticing is your reflection point goes back up to like just barely touching minus 20 or 30 thereabouts. And what you want to do is get to minus 40 at least. For me, that's at least a good indication of a good impedance match at the desired frequency. So I'm just going to trim off half a millimeter here. It starts getting very sensitive. Oh. There we go. Now you can see how close we're getting to the actual frequency of desired, and we've got a better impedance match just because I cut off that little bit, the bottom there. Now, you always want to do 1 or 2 or 3 scans at least, because these things are not as accurate as your proper lab grade equipment, but they get close enough. And what we can do to average it out a bit is actually add a bit of smoothing over here. So most of these VNAs has got a button or a setting where you can add some points, which just acts like a filtering or averaging filter. So we'll just add like maybe 2 or 3 points per point on the graph. And we'll just scan it again. And as you can see now, between the 2 different scans, all of a sudden we're almost at our desired frequency. Now I can go ahead and stop here. And so there we have it. Now, was this a perfect tutorial video for what we needed to do? No, it wasn't, but that wasn't the point. What I wanted to do was illustrate what to look for when testing this actual antenna at your desired frequency. Because I see a lot of tutorials, a lot of calculators, as you can see, that gives you the figures, and a lot of people unfortunately will just carry on building the antenna and immediately give the antenna a bad name simply because the antenna is not actually matched to where it needs to be. As to illustrate that point, if you recall the numbers we looked at, I think it was 89 millimeters for the radials and 82 millimeters for the desired element. And after we've tuned this antenna to the desired frequency we want to be, we are actually at 84 millimeters for the radials and 72 millimeters for the main antenna to get to the desired frequency. So you can see the discrepancy just in using what I call almost a pure copper wire solid, so very little deviance in terms of performance over there. But what you can do now is actually switch back to your calculator, and remember this trick I mentioned earlier. So what you can do now at the desired frequency is change your velocity factor until the numbers that the calculator displays actually matches your measurements in real life. And why do I want to do that? Well, what that does for you is it actually gives you the true velocity factor of your material that you're using. So what I can do now is next time I can use 0.91 for this type of material, and without actually testing it, get very close results with this type of antenna. So if you're making a 433 megahertz antenna for satellite tracking or for ISM band communication, this is one method you can use to build this antenna. So I hope you found this useful. If you have any comments, any better ways of doing it, I'm always happy to listen. drop a comment below, and until next time, cheers.